This is the 20th video in our series on topology. And in the previous video, we talked about arbitrary products of topological spaces and noted that we could endow them with something called the product topology or something called the box topology. Well, now I want to look at a special case of that setup and then endow this space with a third topology, which we'll call the uniform topology. Let's recall that we called R omega the product as n goes from 1 to infinity of the real numbers. And then we could endow it with the product topology by using the following basis of open sets. And those open sets are of the form U1 cross U2 up to UN, and then cross R, cross R, cross R, so on and so forth. The important thing here is that there is a point after which all of the terms there are just all real numbers. And these UNs are all open in R. But we contrasted that with the box topology, which is just simply the product of a bunch of open sets in R with no restriction. And now, in order to create our third topology on this space R omega, let's introduce a metric. We won't check that it's a metric, but I'll let you maybe check it's a metric on your own. That'd be a nice homework exercise. So for x and y in R omega, so that means they're really sequences of numbers or infinite tuples, if you will. So we've got x is x1, x2, x3, so on and so forth. Y is y1, y2, y3, so on and so forth. So we'll say the distance from x to y is the supremum of the minimum of the absolute value of the difference of xn and yn with the number 1. And this is as we range over all natural numbers n. So notice that this set will have a supremum, and that's because this set is upper bounded by the number 1. I think that's pretty clear because here we're taking the minimum of this distance and 1 just to kind of get off the ground. So I'd like to start with a little bit of an example where we calculate the distance between 2 points and just really get our hands dirty with that kind of calculation. So let's say that x is equal to perhaps this. So it'll be 0 and then a half and then 2/3 and then 3/4, 4/5. I think you can probably see where we're going. So in other words, the nth term here is, let's see, it's going to be n minus 1 over n. Okay. And then, well, let's take the other term to be 0. So I'll just say 0 is 0, 0. It's the so-called origin in R omega. Okay, but now let's do our calculation here. So our distance from x to 0 is, well, it's going to be the supremum of the minimum of, well, let's see, we're going to take the difference between each of these coordinates. But notice that the difference between the nth coordinate of the first one and the nth coordinate of the second one is simply this n minus 1 over n. So it's going to be the minimum of n minus 1 over n and the number 1 as we range over all natural numbers. But of course, this minimum is simply our n minus 1 over n. That's because n minus 1 over n is less than 1. So notice that means that we're taking the supremum of the following set. So 0, a half, 2/3, 3/4, 4/5, and so on and so forth. But I'll let you check that the supremum of this set is equal to the number 1. I think that's maybe pretty clear to see, but again, like I'll let you check that. That's related to something that we did earlier. We found supremums of sets. Okay, so that means that the distance between x and, I guess I should put the origin here, is 1. Now we can start to observe how this is different than the box topology. So notice that this x is most definitely in the product of just infinitely many copies of the open interval from 0 to 1. But notice that everything inside of this infinite product seems like it should have a distance less than 1 from the number 0. But the fact that we're taking the supremum here, we get the distance is exactly equal to 1. But I guess what we're seeing here is that this product right here is not equal to the ball of radius 1 centered at 0. In other words, the unit ball of radius 1. Let's recall what that is real quick. So that's going to be all y in r omega, where the distance between y and 0 is strictly less than 1. And we see that these are not equal because, well, x is in this one, but it's clearly not in this one because the distance is exactly equal to 1. Now, I'd like to maybe contrast that with what would be going on if we took a finite product. And in fact, in a finite product, this uniform topology would coincide with the box topology. It would actually also coincide with the product topology as well. Okay, so now I want to show some sort of relationship between the open sets of these three different topologies. Okay, so now we're going to prove a pretty classic result, and that is if we have an open set in the product topology, then that set is open in the uniform topology. And then if we have an open set in the uniform topology, then that open set is open in the box topology. But then we'll also show that all of these topologies are different. So that means that we'll also show that we can find a set that's open in box that is not open in uniform. And we'll also find a set that's open in uniform that is not open in product. Okay, so of course for these implications, we need to do that with a general open set. So let's get going there. And actually, I guess I should say before we start that we don't need to really do it with a general open set. All we have to do it with with a basis open set. Okay, so let's do this first thing first. This open in product implies open in uniform. So let's suppose that we have U1 cross U2 cross all the way up to UN, and then cross just a bunch of copies of R is open. And it's open in, well, pretty clearly the product topology. And so what does that mean? Well, that means that these U little n's are open in R given the standard topology on R. Okay. So now let's note that if an x is inside of U, then that means that xi is in ui for all I, which go from 1 up to n. And then after that, so xn plus 1, so on and so forth, are kind of unrestricted. They just come from the real numbers. So now we'll use the fact that we don't have a restriction past this point in. That'll be really important here. Okay, so now let's notice that since xi is open in ui, that means that there exists a delta I which is bigger than 0, and this is for all I between 1 and n, such that the interval xi minus delta I to xi plus delta I is totally contained in ui. So there we're just using the definition of openness in the real numbers. Okay, so now what I want to do is set just normal delta equal to the minimum of delta 1, delta 2, up to delta n, and the number 1. So you will see that it'll be important to put the number 1 in there. And now to finish this thing off, what we want to show is the following. And that is that the ball of radius delta centered at x will be contained inside of U. That's what it would take to show that this U is also open in the uniform topology, assuming that it was open in the product topology to start with. So we'll do that just by chasing elements from one side to the other. So let's take a y, which is in the ball of radius delta centered at x. But now let's notice that that means that the distance between x and y is less than delta. But notice that means that the supremum of the minimum of the absolute value of the difference of xn and yn with the number 1, as n runs through all natural numbers, is less than delta. Okay, but now let's observe that means that the absolute value of xn minus yn is less than delta. So why did we not have to take this 1 into account? Well, that's because that delta was, let's see, less than or equal to 1. But now let's observe, this means that y sub n is in the interval xn minus delta to xn plus delta, but that's a subset of the interval xn minus delta n to xn plus delta n, which is contained inside of u. It's a subset of that because our delta is less than or equal to each of the delta i's or delta n's here. But then let's see, starting here and ending here, well, that should be a un, and putting all those coordinates together, that tells us that y is in fact inside of u. So let's see, we started out with y in this delta ball around x, and we ended with y is in u. But that's what we need for our u to be open in the uniform topology. Okay, so we did this first implication. We started with an arbitrary set open in the product topology, and we proved that it was also open in the uniform topology. So maybe we'll just go ahead and put a check mark here to say that we've done that. And now let's move on to the next implication arrow. All right, so now we want to show that if it's open in the uniform topology, or we have an open set in the uniform topology, that set is necessarily open in the box topology. So let's say we've got a non-empty open set in the uniform topology. Of course, if we have the empty open set, it's pretty trivial, so we might as well start with a non-empty open set. Okay, so now let's take an x, which is inside of u. And now what we want to do is use the fact that it's open in the uniform topology. So that means that there exists an epsilon, which is between 0 and 1. I'll take it between 0 and 1 here. Well, we can always take it bigger than 0, and there's no harm in taking it less than 1. And that's going to be useful here because of this minimum part with 1. Okay, so anyway, we've got this epsilon between 0 and 1 such that the ball of radius epsilon centered at x is contained inside of u. So again, that kind of thing is possible because we are open in the uniform topology. Really just open in any metric topology here. Okay, so now what we want to do is consider the following set, and I'll call it V. And what it'll be is the product as n goes from 1 to infinity of the interval xn minus epsilon over 2 to xn plus epsilon over 2. So let's see what this is. So this is an open neighborhood of x in the box topology. Okay, great. Now what we want to do is, or maybe we should say that down here, to finish this thing off, what we'll want to show is that V is contained inside of this ball of radius epsilon centered at x, which is contained inside of u. And that will have done it. Because how do you show that something is open? Well, you take something from the set and then you find an open neighborhood that contains that point that is within your set. So here we're open neighborhood necessarily comes from the box topology because we're trying to show that this is open in the box topology. Okay, so we'll show that V is a subset of U simply by, again, chasing elements through. So if Y is an element of V, then what does that mean? Well, that means that Y sub n, assuming, I guess, we're using throughout that Y is this sequence Y1, Y2, so on and so forth, then y sub n comes from the interval xn minus epsilon over 2 to xn plus epsilon over 2. So something like that. That means that the absolute value of xn minus yn is less than epsilon over 2 for all n in the natural numbers. Great. I guess another important thing here is that that is less than, well, less than a half, but less than 1 more particularly. Okay, so now let's take the distance between x and y. So that's going to be the supremum of, let's just put in here a bunch of numbers that are all less than epsilon over 2, because it's just a bunch of numbers like this. keeping in mind that when we took the minimum, we chose the epsilon over 2 part because the minimum was occurring with the number 1. But now the supremum of a bunch of numbers less than epsilon over 2 is less than or equal to epsilon over 2. That's why we had to lower that epsilon to epsilon over 2 for this purpose, that when you take the supremum, you turn a strict inequality to a not strict inequality. But importantly, epsilon over 2 is strictly less than epsilon. But notice, the distance between x and y being strictly less than epsilon means that y is in the ball of radius epsilon centered at x, which is a subset of u. But this is exactly what we needed to show that, yes, we were open in the box topology. Now what we'll do is show that none of these topologies are equal. Okay, so now let's get going showing that these produce distinct topologies on our omega. And we'll start by finding a set that is open in the uniform topology, but not open in the product topology. So that shows that this is really a one-sided arrow and not a two-sided arrow as needed. Okay, so we can actually take a fairly simple open set here. Let's take the ball of radius half centered at 0. And so this is pretty clearly open in the uniform topology. It's actually one of the basis open sets in the uniform topology, given that the basis open sets in a metric topology are simply the open balls. And this uniform topology is a metric topology with the metric that we've been working with. So now, by way of contradiction, we'll show that it's not open in the product topology. And so since we're doing that by way of contradiction, let's suppose that it is open in the product topology and then force some sort of contradiction. So if this open in the products topology, then there exists open sets UN in R such that 0, which is just the sequence of all zeros, is contained in U, and we're setting U equal to the cross product of U1 up to UN and then a bunch of R's. Okay, so let's just reiterate what we've done here. If this were open in the product topology, then for every point inside of this open ball, we should be able to find a basis open set containing that point that is totally contained within this open ball. So let's put that totally contained within this open ball over here. Okay, good. And that's essentially what we've done here. We took a point from our set, and then we said there was a basis open set containing this point, which is totally contained within our original set. But now let's note that this is going to fall apart immediately. And that's because if we take the following point, maybe I'll call it x, which is just 0 up to 0, and then a single 1, and then a bunch of zeros. And the important thing here is that this 1 occurs after exactly capital N zeros. So in other words, this is in the n plus first coordinate. So notice that since this capital N is the place that we switch over to just being all real numbers for the rest of the sets, this thing is inside of U. But it's also pretty easy to calculate that the distance from x to 0 here, so this x to this 0, is pretty clearly equal to 1. It's actually kind of the easiest thing to find the distance between when you have a single coordinate that's non-zero and then you have just a bunch of zeros there. Okay, so that distance is 1, but that means that this x is not in the ball of radius half centered at 0. So look at what we did. We found an x inside of our U where that x is not in the ball of radius half. But that means that it's impossible to find a basis open set contained within this set, meaning this set is not open in the, let's see, product topology. Okay, so now let's do the other inequivalence by showing that we can find a set that's open in box but not open in uniform. All right, so now for our set that's open in the box topology but not the uniform topology, let's set U equal to the product as n goes from 1 to infinity of the interval minus 1 over n to 1 over n. So let's just write that out a little bit. So that's minus 1, 1 cross minus half, half cross minus third, third. So the important thing here is that those intervals are just getting smaller and smaller and smaller. So we know that that's not open in the product topology. It's pretty clearly open in the box topology, but we'll show that it's not open in the uniform topology. And we'll do that again kind of by contradiction. So if this were open in the uniform topology, then we could find, let's see, a ball of radius something centered at 0 contained inside of this U. So in other words, there would exist an epsilon between 0 and 1 such that the ball of radius epsilon, maybe centered at 0, is contained within this U. But we can see that this is not possible pretty quickly. So let's take a natural number capital N such that 1 over capital N is less than epsilon. This is something you always do, and we've done this tons of times already. And now let's observe the following. And that is that the element, which is just 1 over n, comma 1 over n, comma 1 over n, it's maybe like the constant sequence of just a bunch of 1 over n's. So that's pretty clearly in the ball of radius epsilon centered at 0, because you can find the distance between this and the origin and see that that is 0. But let's observe that this 1 over n is not an element of, for instance, the interval minus 1 over 2n to 1 over 2n. And that's because it's bigger than 1 over 2n. But that means that our point, 1 over capital N, 1 over capital N, so on and so forth, is not an element of U. And since this ball was created arbitrarily, it's impossible to find a ball centered at 0 contained inside of U. But that means that this set is exactly what we want. Open in the box topology, but not in the uniform topology. Okay, so now that we've looked at this result, I want to look at some classic examples of compact or not compact sets in these different topologies. So for our next bit of stuff, we're going to start with a lemma. And this lemma doesn't have anything to do with products, but it will be applied when we talk about compactness in certain product spaces. So let's say we've got a metric space X, and we've got a subset A of X. Then if X is a limit point of A, then every neighborhood of X contains infinitely many elements of A. Now, before we get started, I'd like to recall the standard definition of being a limit point. And that would be something like this. So X is a limit point of A if the intersection of A minus X with any open neighborhood is non-empty. So let's see, all U neighborhood of X. So the important thing here is that U intersects A at a point other than X. That's what it takes for X to be a limit point of A. So of course, in a metric space, we're going to get something stronger because not only does it contain a point other than A, it contains infinitely many elements of A. Okay, so let's get going. So let's say we've got a limit point of A, we'll call it X. And then let's also let U be a neighborhood, and it's really just any open neighborhood of X. So we've got a neighborhood of X. But notice, since it's a neighborhood of X, then that means that there exists a delta bigger than 0 such that the ball of radius delta centered at X is contained inside of U. That's what it means to be open in the metric topology. Okay, But now let's observe that for all natural numbers n, the ball of radius delta over n centered at x intersected with A contains a point other than x. So contains a point other than x. And that's by the definition of a limit point up there, because x is a limit point of A. And so let's maybe call it something. So let's call it xn. All right, good. And then, well, let's also note this, that xn is an element of U for all natural numbers n. And why is that? Well, that's because the ball of radius delta over n centered at x is contained within the ball of radius delta centered at x, which is contained inside of U. Those are just like smaller and smaller and smaller balls. Okay, good. And now we can finish this whole thing off with a claim. And that claim is, well, we have in fact constructed our infinite set. So in other words, the set of all of these xn's is infinite. And the proof of this is not too bad. And it goes something like this. Let's, by way of contradiction, suppose that it's not infinite. So in other words, the set of all of these xn's is made up by xn1, xn2, all the way up to xnk. It's got, for instance, k elements. And then let's set a number that I'll call delta equal to the minimum of the distance between x and xk. Sorry, maybe the distance between x and xni as I runs from 1 to k. So what am I doing here? I'm taking each of these points right here that make up our now finite set, which we're assuming is finite by way of contradiction, and we're finding their distances from our original point x that we're using, and then taking the minimum of all of those distances. So since we've got a finite number of distances here, we know that that minimum is well defined, and we also know that that minimum is bigger than 0. We know that bigger than 0 is bigger than 0 because all of these xni's are our original xn's, but all of those xn's are points other than x. But that means the distance between them and x is necessarily positive by the rules of a metric in the first place. Okay, so next up what we'll do is find a natural number that I'll call capital N such that delta over capital N is less than epsilon. But note, that means that for all little n bigger than capital N, we have the distance between xn and x is less than delta over capital N, which is strictly less than epsilon. But what did we just do? We found infinitely many points that are all closer to x than the supposed finite number of x's that we're allowed to have. In other words, we have found infinitely many points that are outside of this supposed finite set, which makes up our entire sequence. But there's our contradiction. Okay, so we've got our contradiction. But that means that this was, in fact, an infinite set. But that's what we wanted to prove. Okay, so now let's see how we can apply this for compactness of some products. Okay, so now for the big result of the day. And that is that 0, 1 omega, so in other words, just an infinite product of the closed interval 0, 1 living inside of R omega, is not compact in the uniform or the box topology. Now, we'll start by showing that it's not compact in the uniform topology. And we're going to do that using a result that we previously proved. We'll in fact show that it's not compact or not limit point compact in the uniform topology. But let's recall that we previously proved that if a set was compact, then it was necessarily limit point compact. So that means by the contrapositive, if it's not limit point compact, it cannot be compact. Of course, we should probably recall the definition of limit point compactness, so let's do that. So X is limit point compact if every subset, every infinite subset of X has a limit point. So to show that this is not limit point compact means that we need to find a carefully chosen infinite subset that has no limit point. So let's take our infinite subset and we'll call it A, and it'll be equal to, well, said very briefly, all binary sequences in R omega, which are necessarily in 0, 1 omega. So what do I mean by that? Well, they're going to be everything of the form x1, x2, x3, so on and so forth. Like I said, that's in R omega, such that xn is inside of 0, 1. And by 0, 1, I mean the doubleton 0, 1. So xn is either equal to 0 or xn is equal to 1, and that's going to be for all n. Now notice we could just smush all this together into this set containing 0 and 1 upper omega, and that would be like the same kind of idea here. Okay, so now before we get started, I'd like to make an observation which is going to help us out quite a bit. And that is if we've got 2 points A and B in A with A not equal to B, then their distance always happens to be 1. That's what we're going to show here. But how will we do that? Well, if we've got 2 points from A that are not equal, then that means that there is a coordinate, I'll call it xn, such that, or I'll call it n, where A sub n is not equal to B sub n. So there's a place where they differ. Now, without loss of generality, we might as well say that A sub n is 0 and B sub n is 1. Because the only two choices for that coordinate are 0 and 1. So if they're not equal, 1 has to be 0 and 1 has to be equal to 1. And now let's look at the distance from A to B. So let's observe that that is the supremum of, I would say, the minimum of the difference in 1, but notice that the difference is either equal to 0 or 1. So the minimum of the difference in 1 is just the difference, really the absolute value of the difference. So here we have the supremum of the absolute value of an minus bn as n runs through all natural numbers. But notice that that's going to be the supremum of, well, one of two sets. So if A and B differ everywhere, then this difference is always 1, and you're just taking the supremum of 1. If they differ not everywhere, well then some of those differences are 0, but you're guaranteed one of those differences to be 1. So either way you look at it, this is the supremum of the set containing 0 and 1, which is, well, 1. Okay, so what do we want to take out of this? Well, I think maybe the important thing to take out of this is that if we've got two elements from A that are not equal, then the distance between them is equal to 1. Okay, so now let's get going showing that this set A does not have any limit point. So let's suppose, by way of contradiction, that X is a limit point of A. But what does that mean? Well, by our previous lemma, that means the following. Every neighborhood of X contains infinitely many points from A. So we're using the fact here that our set is a metric space. We know it's a metric space because it's the uniform topology, and the uniform topology is a metric topology. Okay, so now what we'll do is apply this result, which again is from our previous lemma, to a special neighborhood. So that implies that the ball of radius 1/3 centered at X contains infinitely many points from A. So if it contains infinitely many points from A, it contains two different points from A. So let's take A and B from A, where A is not equal to B, and A and B are in the ball of radius 1/3 centered at X. And now we'll see everything go wrong. So let's notice that the distance from A to B is equal to 1 by this observation we made right here, because A is not equal to B. But then that's going to be less than or equal to the distance from A to X plus the distance from X to B by the triangle inequality. But since A and B are in the ball of radius 1/3 centered at X, those distances are less than 1/3. So this whole thing is less than 1/3 plus 1/3. In other words, it's less than 2/3. But notice we've got a big issue here, because what we've done is we've just shown that 1 is less than 2/3, which is a clear contradiction. Contradicting this assumption that we made right here, that it was possible to get a limit point in the first place. So that means we can't get a limit point of A. In other words, A does not have any limit points, but it's an infinite set with no limit points. But if we've got an infinite set with no limit points, then our set is not limit point compact. But again, that means it's not compact. In this case, in the uniform topology. Okay, so now let's move on to explore this in the box topology. Okay, so now we'll show that 0, 1 omega is not compact in the box topology. And we'll do this using the same set that we used before, this set A, this set of binary sequences. So let's take a little a inside of our capital A. So that means that it's made up of A1, A2, A3, so on and so forth, where all of those ANs are either 0 or 1. And now what we want to do is use this set capital A to build an open cover. And we'll show that that open cover does not have a finite subcover. But of course, if we had a compact space, every open cover would have a finite subcover. So doing that shows that it is not compact. Okay, so how are we going to build an open cover out of this capital A? Well, we're going to do it by assigning the lowercase a, every element of A, to an open set. Okay, so how can we do that? So now let's set I sub n upper A equal to one of the following intervals. So this is either the interval from 0 to 3/4, including 0 but not including 3/4, and that's going to be if an is equal to 0, and then it's going to be the interval from 1/4 to 1, including 1 but not 1/4, if an is equal to 1. And then after that, let's glue this all together into an open set in the box topology. So I'll call that open set U sub A, and it's going to be the product as n goes from 1 to infinity of I sub n upper A. So let's do just a little bit of an example here so that we've got some sort of intuition for what's going on here. So U sub, let's see, we have 0, 1, 1, 0, 1, so on and so forth. So recall that every element of A is of this form. So let's see, what is that going to be? So that's going to be the interval 0 to 3/4 crossed with the interval from 1/4 to 1 crossed with another interval from 1/4 to 1, because we have 0, 1, 1. And then we cross that with the interval from 0 to 3/4, and then we cross that with the interval from 1/4 to 1, and then, well, we keep going. So notice the entry tells us which interval we put there. And you might be worried a little bit here because we've got some brackets, but recall that this is all happening in the subspace topology. So this is an open set of bracket 0, 1 upper omega in the subspace topology put on the box topology. And now we're going to make our claim, and that claim is that all of these UAs cover our 0, 1 upper omega. So let's write that down. So here we've got a U sub A, as A runs through all of A, covers 0, 1 upper omega. But let's notice that that's equivalent to saying that the union as A goes over all of A of U sub A equals 0, 1 upper omega. I guess kind of what it means is a subset relationship this way, but since everything in there is a subset of 0, 1, that means we really get equality here. So now how are we going to prove this little claim? Well, it shouldn't be too bad. So let's say we've got an x which is in our space. So it's in 0, 1 upper omega. So, well, what does that really mean? So that means that x is equal to x1, x2, x3, so on and so forth. And each of these xn's are on the closed interval from 0 to 1. Now what we'd like to do is construct one of these u's that contains our point x. Now it shouldn't be too bad, so let's do it. So let's say we're going to construct a b inside of a as follows. So b sub n is, well, it's going to be either 0 or 1. Remember, because A, capital A, is the set of all binary sequences. So it's going to be 0 if xn is inside of the interval from 0 to a half, including 0 and including 1/2. But it's 1 if xn is inside of the interval from 1/2 to 1, not including 1/2. So notice that these two intervals right here union to be the entire interval from 0 to 1. So this gives us a well-defined way of choosing our b. So our b is necessarily chosen to be exactly one of the number 0 or 1. Okay, so now let's note the following, and I think this is pretty clear, and that is that our x is inside of our u sub b. And well, why is that? Well, that's because xn is inside of I upper b, let's see, underscore n for all n. And that's really because if xn is in here, then bn is 0, but then that means in is from 0 to 3/4, but 0 to 1 is contained within 0 to 3/4. It's as easy as that. Now, if xn is here, that means bn is 1. That means in is from 1/4 to 1, but that means that xn is necessarily inside of this in as well because of the containment. So that's how all of this works. But then smushing all that together tells us that xn is in one of these u's. It's in this ub that we constructed. But that ub is pretty clearly a subset of the union over all a in a of ua because it's one of them. But let's see, we started here, x is in this, and we ended with x is inside of our union, but that means that our collection up here does in fact cover 0, 1 omega. So now we just have to show that it does not admit a finite subcover. All right, we just showed that we did have an open cover of 0, 1 upper omega. Now we'll show that this cover does not have a finite subcover. And that means that, well, we've got an open cover with no finite subcover, meaning that in the box topology, this space is not compact. And so let's see how this little proof goes. So it's going to go by way of contradiction. So by way of contradiction, let's suppose AU1 union up to UA1 unioned up to UAK is 0, 1 upper omega. So in other words, we're supposing we have a finite subcover. Okay, so now let's note the following, which I think is pretty clear, and that is that A is inside of U sub B if and only if A equals B. Well, let's see it. So let's note that if A is in UB, then that means that AN is inside of I upper B, let's see, under N for all N. But now let's see, if B is equal to 0, that means that AN is on the interval from 0 to 3/4. But it's also only can be equal to 0 or 1. So the only thing that could be between 0 and 3/4 that's also equal to 0 is 0. So that means that AN is equal to 0. And then, well, if BN is equal to 1, then we similarly get that AN is equal to 1. That means that AN and BN are always the same. meaning that A and B match in every entry, meaning that A is equal to B. And I think the reverse direction is very, very clear. Okay, so, well, what does that mean? Well, that means that A is simply equal to this set A1, A2 up to AK. Now, well, why is that? Well, since this finite cover or finite subcover covers the whole space, then it also covers our set A here. But if it covers our set A, that means that A can only have finitely many elements because of this rule that we just proved. But of course, A has infinitely many elements. And we can list infinitely many of them pretty easily. So we could have just 1, 0, 0, 0, 0, so 1 and then a bunch of zeros. You could have 0, 1 and a bunch of zeros. You could have 0, 0, 1 and a bunch of zeros, so on and so forth. So you could just think about all of the elements of A that have a 1 in exactly one spot. There's pretty clearly infinitely many of those. But here we just showed that A was finite. So that's our clear contradiction here because A cannot simultaneously be finite and infinite. But that means that our cover had no finite subcover. But that means that our set is not compact in the box topology. Now you might say, well, what about in the product topology? Well, in fact, this is compact in the product topology. And that's something that we'll get around to proving later. But now let's leave you with some exercises. Okay, here are a couple of classic exercises involving these three topologies. So the first is to determine the continuity of certain functions in product, uniform, or box topology. So all of these functions go from R to R omega. So the first one takes x to x, 2x, 3x, so on and so forth. The second takes x to x, 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 so on and so forth. And the third takes x to x, x over 2, x over 3, x over 4, and so on and so forth. So then let's determine the convergence of some sequences in these topologies. And I won't read these off, but here are the sequences to explore. And that's a good place to stop.